Okay, so I'm going to talk about genetic algorithms. And I first encountered genetic algorithms with, by watching this video. This is from '94. I'm going to play a little bit of it for you. This is a project called, I'm going to just turn the sound off, although this is a project called Evolved Virtual Creatures. Actually, the nice thing, I encourage you to Google this and watch it. It's Carl Sims' Evolved Virtual Creatures. And the audio soundtrack is kind of nice because it's like a National Geographic style video, but it's all computer-generated creatures. So what Carl Sims did with this project is create essentially this physics framework for making these creatures. They're all these node-based creatures. So all of these creatures are essentially, if I were to diagram them, they're kind of, you can think of them as particles with spring connections in a way. So they're boxes. And these spring connections are muscles, and they can expand and contract. And so Carl Sims was able to encode the design for these creatures into a virtual DNA, and then say, hey, let me stick them all into this physics world and see how they do. The ones that run really fast, jump really high, swim really well, there's a water simulation in a little bit, those are the ones that I will pick as parents, quote unquote, to make a strange virtual creature baby for the next generation. And they'll get, the better that they do, the more likely they are to reproduce. And he evolved these creatures to perform different tasks. And so looking at this, I was looking at this at a time where I was super fascinated with even just trying to model kind of basic physics. And so I wanted to see if I could make something like this. Yeah, this is the running sequence. This is the jumping sequence. Skip ahead a little bit. This is following a red dot while swimming. And what's really amazing about this is it's very unexpected. Like, you would never design a creature to look like that or do like that. But this one is very, very good at kind of swimming around in this water environment. And at the end here, there's this like hockey-like competition where all these different creatures try to compete for this green cube. So
he would build these algorithms and then like kind of set them up in this like physics 3D environment, and then have to like churn out frame by frame what would happen.
Right. So, I don't know. That's a good question. I don't know the exact process that he used, because in theory, you don't need to watch the simulation in order to find out the result. He might have just but we're watching certain creatures that were evolved and then seeing them play out. But it's all just data. It's all just numbers. And that's kind of what I wanted to get to into a description for how this worked. And it's like funny, they have all these weird gestures. But there's a great, all of this is linked, they're on the Nature of Code website. There's a further reading section, and there's a paper by Sims which outlines how all this works and the design of these creatures. This one's a cruel one that likes to beat up on its so that I'm really not doing justice to the soundtrack. It's really quite nice, but you can watch that on your own time. Okay, so what I wanted to start with is kind of talking through, okay, so the thing about genetic algorithms is, for the book, I kind of divided my thinking into three different categories. Let me just erase this, there is this, genetic algorithms were developed for solving certain kinds of computer science problems. Search problems where a brute force method is no good. So if you need to check every possibility, it would take too long. Maybe we could evolve towards the right answer. And then there's this category called interactive selection, which is really used in art and design, and I'm going to show you some examples of that. And then this idea of thinking of ecosystem simulation. So what I wanted to talk about first is the now it looks like I have a prepared presentation, but these are just images from the book. But so I wanted to talk about the infinite monkey theorem, which is kind of a classic test case, classic example of an application of genetic algorithms. So the infinite monkey theorem, if you're not familiar with it, is this idea that, if we had an infinite number of monkeys and an infinite number of time, and they're all just randomly typing at these keyboards, typewriters maybe, keyboards, iPads, I don't know, that eventually they would type the complete works of Shakespeare. And so this is theoretically true, I suppose, I believe to be true. Yes, it is theoretically true. But the problem is, it's not something we could ever understand or experience in our lifetime. And just to make this argument for a second, so let's say we have just the phrase "to be or not to be," that is the question. That phrase is 39 characters long. So let's say we have a simplified keyboard. It only has 26 characters and 1 spacebar. So just to type a T, there's a 1 in 27 chance of typing a T, right? Now, if you know anything about probability, event probability, if we want the probability of 2 events happening in sequence, we multiply the probabilities together. So the chance of typing TO is 1 out of 27 times 1 out of 27. So the whole phrase 1 over 27 to the 39th power is a 1 in that big number, a chance of that occurring randomly. So that's a very large number, which is kind of hard to even fathom. But that's not even for the complete works of Shakespeare. That's just for to be or not to be the question. So, and I worked it out a little bit with that. If there's a similar discussion, by the way, on Wikipedia. If you go to Infinite Monkey Theorem, which kind of goes through the same sort of stuff. But if you were able to have a computer simulation that could do 1 million random phrases per second, it would take that many years for there to be, I don't think I put this up here, for there to be a 99% probability that you would have at least gotten to be or not to be. That is the question somewhere in there. So if that's much longer than the entire, much longer than the age of the entire universe. I think like on Wikipedia when I was reading it the other day, it said something like, if you had a monkey for every atom in the entire universe, it would still take, anyway, just way too long that we can't possibly understand. So the point, this is a stupid problem, right? Because we could just type to be or not to be the question, that is the question if we needed it. But it illustrates the point that there are some problems for which you don't know the answer. Like we know the answer here. Some problems that you don't know the answer for which it still, it would take that long by brute force method. So a genetic algorithm is a way of saying, okay, what if we had a population of phrases? So let's just say, to simplify for a second, we're trying to evolve the phrase cat, and we had a population of phrases like bad, car, I don't know, hog. It's very hard to think of. I was going to say pea as a 3-letter word. I don't know. I can only think of like weird, uncomfortable words. Anyway, a bunch of hat is good. What?
PEA, you're all good.
What? PEA, thank you. There you go. Okay, so a bunch of phrases. What we could do is evaluate these. So the way the genetic algorithm works, and I think I have, I like to sort of write this out, but I'll just use these. There's this very specific algorithm, and I'm using, by the way, the words setup and draw are things that are very specific to processing. This algorithm works where there's kind of this moment of like the Big Bang happens, and there's this initial population that's seeded, and then there's something that happens over and over again. A new generation is born, evaluated, a new generation is born. So the very first thing so one of the things I should mention is that if you look at Darwinian natural selection, by the way, I don't really know anything about biology and evolution. So, and that's the nice thing about doing this stuff in like, computer programming. You can't just like make it up and I'm like inspired. It's like the TV shows where they say inspired by actual events. That's what this is. It's not.
Inspired by actual science.
Yeah, inspired by actual science. So there's heredity, selection, and I would like to write first variation. So if you think about Darwinian evolution, these are 3 key principles that need to be present for evolution to happen. One thing is that we need to have variation. So we would never be able to get to be or not to be if we just had one phrase to start with. And all we could ever do is combine and recombine that one phrase. We'd only ever have that one phrase. If we only ever had bad, we could never get to cat. But if we have a random, if we seed our initial population, that's the first thing we do, with a random set of elements, then we have variation and we have the chance to evolve towards some optimal solution, so to speak. So, one of the other principles that we need is this idea of selection. So selection, often referred to as survival of the fittest. We have this idea in nature that, the most fit, the strongest, the thing that can run the fastest will, make the most children. But really what it is, if you think about it, is just survival of the survivors. Anything that lives longer for any reason whatsoever is more likely to reproduce. So, that's nature. And here, what we actually unfortunately need to do in this particular computer simulation is we need to calculate fitness. So this is a mathematical formula that we're going to apply to these members of this population. We're going to say, we're going to evaluate their fitness, and this is how we perform selection. Once we've evaluated the fitness of all these elements, we can pick the ones that should be selected to be parents. So for example, a really simple fitness function for these would be count the number of characters they got correct. BAD, 1. CAR, 2, got 2. HOG, 0. Hat is also 2. P is 0. So you can see, oh wow, this worked out really well, by the way. by accident.
So it's not just
yeah.
the character choice, but its position.
Yes. So, this is an open, interesting question. In other scenarios, the actual data could matter and could be, but this having an A, the way the algorithm is going to work, having an A in the first character would do us no good. We're not shifting them around. That is a sort of discrete chunk in that particular order. So now we have this question of what we're going to do. What we need to do is make the whole goal of this is to make the next generation. So what is the next generation of, I don't know what to call these, creatures. It's kind of silly to call these phrases. So the members of our population are phrases. What is the next generation? We have to figure out a way to pick them. Now, there's a lot of different strategies for performing selection in this type of simulation. We could just say, I don't care, pick the best ones. Car and hat, you make all the babies. So car and hat just reproduce and make all the members of the next generation. We could do something where we take the top half. There are different strategies. A common strategy, which I think in many ways is the best, is a probabilistic approach. So what we could do is assign the fitness values to be probabilities. And we could say, unfortunately, P has a 0% chance. Hat has a 40% chance, 0% chance, 40% chance. Yes. 40%, 20% chance. And if we add all those up, we get 100%. Yes, good job. OK, so you can see how I'm mapping these scores to probabilities. And typically speaking, you're not really going to have fitness values that are this simple, which you're having just 0, 1, and 2. So you're going to have a much more of a range of probabilities. And this is really key, because in a longer phrase, we want to keep. It's possible that this one, let's say, OK, bad here, even though it only got one right, it could have a gem in there that isn't anywhere else in the population. And we want, even though it should be less likely than car or hat to be picked, it still should be possible that it should get picked. And I think, kind of jumping around here, but here, so this is kind of an illustration of that. You can think of it as all of the parents being this roulette wheel, or this wheel of fortune, where you spin it. And what we're going to do is now, over and over again in our genetic algorithm, to make the next generation, we're going to spin it twice, pick 2 parents, and we're going to make a child element from those. And if we go back to this algorithm, it says so the next thing is reproduction. Variation we got from initializing the population, selection we get from this sort of awkward thing that I described of evaluating all the members of the population, giving them a score, then assigning those scores to probabilities, and that's how we pick the next members. Now we need to reproduce, and this is where the third principle of evolution comes in, which is heredity. We need a mechanism for passing the genetic information down to the next generation. This may seem obvious to you, and the point of this example is that it's simple enough that hopefully this can seem somewhat intuitive and obvious. But if you had to combine hat and car, we could look at this and say, aha, take the C from here, take the AT from here, put those together, and we have cat, we're done. But again, we're not taking a top-down approach here. What we're doing is 2 things. One is called crossover, and one is called mutation. And I think one of these diagrams, one of these diagrams just demonstrates this idea of crossover. So crossover, so if you've done any programming, you know something called an array. An array is a list of information, and usually in my examples at least, the DNA is encoded into an array of information, an array of characters, an array of floating points, an array. A true genetic algorithm would be all just zeros and ones, and that's all it ever is, because it's much cooler that way or whatever. But here we could say. What we're doing is we're picking half of one and half of the other. We could alternate. We could sort of flip a coin for each gene, so to speak, for each element of the array. Heads pick from the left, tails pick from the right. We could pick a random midpoint. There's a lot of other options. But that's the first step.
So the idea is to intermingle the genes of the parents into a new generation.
Correct, exactly. And now we get this next, we get this, and in theory, we're picking parents that have performed well, and by recombining their genetic information, we're going to get a child that will perform equally well, or hopefully by luck a little bit better. But we want to add one more step here, and this is kind of important, because even though we got variation in the first step by making this random population, we might not have enough variation, right? If we only have a population of 50 elements, and we need to evolve to be or not to be, there might not have been one with T as the first character. And with crossover, if there's no T as the first character, we'll never ever get to be or not to be. But what mutation allows us to do is say, at any point, there is a small probability that after crossover, one of the genes, so to speak, one of the elements of the array of the data would just randomly change. So here we could say, you can see here in this diagram, we got F-O-R-Y, and we changed it to Foxy, I guess. So we sort of flip a coin again. And typically a mutation rate would be something like a small probability, 1%, 2%, somewhere around there. So we say there's a 1% chance of just changing one of those elements randomly, and that introduces just additional variation into the system. Does anybody want to ask any questions? Okay, let's see here. So I'm going to come back to this, but let's just look at, I'm going to run this example now. So if I go into my chapter 9 examples, there is one example called G.A. Shakespeare, and I'm just going to run it. And this is currently running basically this simulation that we talked about in processing. So you can see on the right, left, right, on the right, I'm going to just do it this way, Stage right, yes. All of the current phrases in the population, there's 150, they don't all fit into the window. After 764, we started with 150 random phrases. There's a mutation rate of 1%, and after 764 generations, one of them happened to be exactly right to be or not to be. Some things that I would just want to kind of quickly demonstrate here is that, again, the point of this example is not that this doesn't have any value, right? I could solve this problem in one line of code. Print to be or not to be, that is the question, right? The point of this is, if we want to sort of learn about genetic algorithms and understand how they work, we need a kind of example where the answer is unbelievably obvious. So that's what we're kind of demonstrating here. The other thing I just show you is that there's various variables that we can kind of play with. Here, for example, if I were to suddenly just make the population 1,500 instead of 150, we got to be or not to be in 38 generations, because we just have so much variety to work with. So the other thing that I wanted to demonstrate here is if I make the mutation rate 0, and the population only 150, this isn't enough variation. For example, we can see here there clearly was no second character ever that was an O. There was no fourth character that was a B. So we're just sort of stuck in to keys of a B or whatever. But so this idea of mutation is really important. But of course, if we had 1,500 elements, again, that's probably enough variety, and boom, we got it right there. So it's kind of, it's sort of, you can play with some of these variables. Total populationation, that's a typo. Somebody do a pull request to fix that. There was something else I wanted to show here. Yeah, okay, so one of the other things I think is important to see, like, even if I make the mutation rate 10%, like, that is introducing so much randomness into the system. It's too much randomness. You could think about it, it's likely that we're going to be randomly changing a character almost in every new member of the population. So, and to illustrate the point of that we need a lot of lifetimes of the universe, if I made the mutation rate 100%, right, this is the brute force method. We're sitting here doing, essentially 150 times 30 per second random phrases, and there could be some kind of like amazing moment here where we actually got it, but.
And then we realized it.
Then I'm going to go buy some lottery tickets if that happens. Okay. Yeah.
In this case, what it's doing is it's just thrashing it with the whole phrase, and if it doesn't get the whole phrase, then it just moves on.
Well, right now it's actually running through the genetic algorithm, but we've essentially negated the genetic algorithm because at the very last step we said, I don't care what evolution you did, I'm randomly mutating everything. So it's as if we're just newly picking random elements every time. So I think I'm sure there are lots of applications to this, to solving different kinds of, standard computer science problems, data-related problems. The direction that I went in with the examples in the book is really in the animation and simulation direction. So I want to talk through a few elements. Oh, there's an eraser here I was using. I want to talk through a few elements. Talk through a few other examples, and then I think we can answer some questions and wrap up or whatever. So one thing that I kind of glossed over here is again, I don't know anything about actual science. There is something, if you read about this kind of stuff, called a genotype and a phenotype. And one thing, this is a really important distinction that's actually sort of secretly happening behind the scenes here. Genotype we can think of as the data itself, right? The actual raw encoding, the bits, the DNA itself. Phenotype is the expression of that data. And in this particular example, this distinction is blurred. There is no distinction here because the data is the phrase cat. The expression of that is, oh, the phrase cat. But when you actually go to use a genetic algorithm in a more of a real world scenario, if you think of that Carl Sims video that I showed, the data might have been this kind of network diagram, data structure. The expression was this kind of visual physics simulation. We need to be able to have a mapping towards what is our system? Is it something visual? Is it behavioral? And how do we encode that into data? And this is, in many ways, if you look at these examples and you want to do a project with them, you can just copy paste the code verbatim. The two things, there's probably three, I'll think of more. The things that you really have to think about are the fitness function. What is that? A good fitness function makes a genetic algorithm work well. And then how are you encoding the data and how are you expressing that data? So there's a project from many years ago by Jer Thorpe called Smart Rockets. I think I have that somewhere here. Okay, I'll hit OK. And this is done in Flash. I believe it's on the web. I'm sure you can just Google Smart Rockets Jer Thorpe and find it. It's also referenced in the book. But excuse me, what's happening here, and again, this is just a search problem, by the way. What's happening here is there are these rockets that launch from the bottom. And the rockets launch from the bottom, and they have each rocket, I might botch this slightly, has like 5 thrusters attached to it that thrust in random directions. So they're vectors, they're forces that can thrust out in random directions. And the DNA, the genotype is the sequence of how those thrusters fire. The expression is the actual physics simulation of them moving. So if you think about it here, these rockets, their goal is to reach the target. And their fitness function in this case is how close did they make it to the target? So inversely proportional to the distance. The closer they get to the target, the higher the fitness. So the ones that do better pass their genetic information to make new rockets for the next generation. And if you run this over time, you'll see these rockets start to evolve this really nice swooping path around that obstacle in the middle. And there's some nice design elements here. You can sort of see this path over time. So this is a nice example of kind of taking a genetic algorithm. We could say like there's a known solution here, which is like I could go, I don't want to mess up the screen, but I could go and draw a path. Like we could figure out possibly but here we could imagine this being part of it. Some type of simulation, a game, a museum exhibit, some interactive experience where the elements are evolving a certain behavior. If you were to move the obstacle around, they would have to re-evolve a new path. And I'm going to show you some examples like this in processing. So the second example I have in the book is essentially a simplified. So Jer's has a lot of bells and whistles for looking nice and doing extra features. In the book, I have a very simple. I think it's this one that I want to look at. Very simple implementation of it. It's much uglier, less interesting to look at. I put that eraser somewhere. Here it is. So the thing that I just wanted to mention here is that we have this question we have to answer, which is that DNA, as we saw, we think of as this list of information. It could be zeros and ones. It could be, as we saw, characters. I don't know what I'm writing here. In this case, one of the things that's interesting about a couple of my examples, or I like to think is interesting at least, is that the DNA is vectors. So it's directions and magnitudes, velocity vectors, force vectors. So each one of these rockets has a kind of sequence of vectors that control its path, and they're evolving. These take a little while to run, but if we ran it for a while, it would evolve sort of this path around that target. I'm going to quickly,
So like when they die and then everyone's evaluated.
Yeah, okay, so I'm kind of meant to get to this, but I'll just mention this for now. So you may be wondering, boy, this doesn't seem very natural. This is like this absurd way of thinking about evolution, right? If we were to map what we've just done here or in the to be or not to be into the real world, it's as if we'd be saying, okay, let's evolve some monkeys. Let's get 20 monkeys in this room. Let's have them run around for a while. We'll give them hats. We'll put a score on them. And then we'll tell which monkeys to mate. And then they'll have babies, and we'll kill all those monkeys and let the next monkeys run around. So the real world is much more fluid. There's no scoring. It's just, so that is... that is, I think, a sort of important distinction here. And the next... I was going to say the last example that I have to show you kind of asks that question of could we do a more fluid simulation where just things that live longer somehow through whatever arbitrary parameters are more likely to then reproduce. So yeah, it's a little weird, but you're right, that's what's happening. I'm letting the simulation run. It gets to the times out. I evaluate them, make the next generation. Just to show you one more example, which is basically the same thing, but a little more interesting just in terms of the technical implementation. So this is exactly the same thing, just a lot more rockets, and I'm visually just showing you the one that's kind of doing the best, that generation, and there's no obstacles here. One thing I want to show you about this, in the previous example, each object's DNA was a linear list of vectors. In this one, their DNA, what's in their brain is actually a flow field. So a flow field is a two-dimensional grid of vectors. You know, those, you can't tell which is pointing forward or back in what I'm showing you here. But so each one of those triangles is essentially looking at an arrow that sits underneath itself, which tells it which way to move. And in theory, if we ran this for long enough, what we would evolve, hopefully,
I think you got it.
Is just a lot of lines that point straight across. And one of the things that I think is kind of interesting to play with this example is I can kind of draw obstacles. So if I draw a little obstacle here, that blocks them, and you'll see it engage kind of in the next generation, and they'll start to evolve a path around it. Maybe what I'll do is draw a few obstacles here, and then I'll let them, oh, that's going to be way too hard. They didn't get very far in the first place. But anyway, so you'll see once one gets kind of far, it'll start to, a few more of them, the next generation will kind of get there. There's a lot of randomness at play here. I actually have the mutation rate very high in this particular scenario because I find that this is a difficult enough problem that there needs to be a lot of random fluctuation to get around these kind of corners. So I'll try to let this run as I continue to show you some more other things.
The fitness thing is kind of picking out the best guy until he dies.
Yeah.
So like right now he dies and then it picks another one?
No, you know what? I'm just highlighting whichever one is currently the best.
Oh, okay.
So it changes over time. You know, it was that one for a little while, now it's that one. So I'm glad you mentioned that. So this idea of genotype and phenotype is important. The fitness function is also really important. One thing I didn't mention is that our fitness function for to be or not to be, that is the question, was actually not a very good one. Just counting how many characters are right isn't very good, and I'll try to explain to you why. Let's say the target phrase was 8,000 characters long, and we had one member of the population that got 7,000 correct, and one that got 7,001 correct. If we evaluate these, if we turn these two numbers into probabilities, the probability of picking one or the other is going to be very, very, very similar. But 7,001 is really a lot better than 7,000. So you'll see in a lot of these examples, and I think I have a very, very basic illustration of this, right? That in a lot of the examples, if you go look at the code in the actual fitness formula, that we were mapping the number of characters correct exponentially. So whether we squared or said the power of this or whatever, so that the more characters we get correct, the higher the score is exponentially. So a linear mapping of number of characters correct to score, and the same thing with distance. So it's something that you'll see in a lot of these. How you tune that fitness function can really affect how the system behaves. And let's check on these guys, because I'm afraid it's going to quit and we'll be very sad. Oh, you know what? It's running really slow because I'm drawing all those lines in the background, which we don't need to do. Let's see how well they're doing. Pretty good. So you'll see they'll make it there eventually. I also am not giving them a very long amount of time to get there. It cuts off before. So I probably should have tweaked those variables as well. But OK, so Yeah, and in this case, I'm also, the other thing I should mention, it's you feel like really attached to these little creatures. Maybe that's just me. Another thing I wanted to mention here is that one thing I'm also doing is they haven't reached the end yet, but when they reach the end, I keep track of the order of them. So who was first, who was second, who was third. And if you were first, boy, your fitness is much higher. That way they, in theory, they would optimize towards the fastest path as well. Okay, so
close, don't change it.
yeah, no, I'll let it run. We'll come back. You guys really want to watch this? Okay, I'll let it. Okay, so the last thing I wanted to mention is, and for those of you who are doing stuff on the web or web developers, this is probably where it might get even more relevant, possibly, I don't know. All of these examples I've shown you so far have taken an algorithmic approach to fitness. It's a mathematical function. We're scoring the elements. But we could take a different approach, which is often known as interactive selection, where we say fitness is user-driven. So in other words, by that I say, hey, and so apparently all I can use is Carl Sims as my examples, but Carl Sims has a project, an art installation from many years ago, called Galapagos. You can see how old this is by, there's
The state of the art.
The state of the art. Okay, so this is called Galapagos, and there are these monitors in a kind of gallery space. There's sensors on the floor, and they're showing these images. And as anybody stands on one of those sensors, it registers a value. And what it's doing is it's assigning fitness based on how long somebody is looking at something. So it makes there's a kind of open question here, which is that, what is that really evolving? The most beautiful image, the thing people are most likely to stand in front of? Who knows? But it is an interesting technique for saying fitness is user-generated. It's evaluated. And the one thing about this is, in to be or not to be, we could do thousands of generations per second, right? Frames of animation, computer calculations. This type of thing is very, very slow. People have to stand in front of it over long periods of time. In a public space over years, maybe you could get some data. The place that I think something like this could really work is on the web, where you have a distributed way of saying, hey, world, everybody, quick, assign some fitnesses, and we could evolve something, maybe. Anyway, it's the SETI at home kind of approach of the mass audience kind of helping at a single problem. So. And also, these are what the images look like. I think they were all these Lisp sequences. Anyway, so I wanted to show you just briefly a kind of simple. So here is interactive selection is really interesting. I've seen people do it with music, with images. I saw a project which was evolving cell phone ringtones. But here I have what might possibly be the lamest example of interactive selection ever. But just to demonstrate the point, these are a bunch of designs for faces. There's data here. The data is color, size, position, width of the mouth. And what this example does is it allows you to say, okay, I really like green, so I really like this one. I'm giving that a much higher score. When I evolve the next generation, you can see, I did that in a very, I only rated one of them, but I could say I like this one a lot and this one a little bit. And you can see I'm starting to mix and match. There's some mutation in there. So again, there's nothing particularly exciting visually about this, or even that creative in its thinking, but it demonstrates the process of creating a visual based on data. And one of the things about this example is that the DNA, this is a kind of a nice technique, every element in the DNA is just a floating point number between 0 and 1. One thing that's nice about that is you can always map a number between 0 and 1 to any range. So I could say, this is the red value, and I map it to 0 to 55. This is the green value, 0 to 55. This is the eye size. I map it from 10 to 20. So you can have this kind of generic DNA where everything's a floating point value, and then map those values to the design of something. I would say if you're looking to create a design, thinking of a node-based approach or parameter-based approach, there's lots of other possibilities there. Okay, so I think I'm kind of nearing the end of time. Maybe we have the to be or not to be. That's the question by now. Let's check on. Is that the same one? Yeah. Oh yeah. See.
It's too bad it's not highlighting the guy that actually.
Right. So you know what? The problem with that is I don't know which one's going to get there. So I could run it twice.
Right.
Like I could zoom through it, figure out which one it is. It's funny, I actually just added made this example, most of it this afternoon. So
I mean, what's so cool about this is that the guy that ends up winning is not the winner for like the first third of it.
Right. Yeah, there's a lot of mess going on here. And what's interesting, what's interesting about this is that, there's really only a small number of vectors that are really at play here. All that stuff in the corner, it's not being used. It's only just random, because anyone going up there is kind of lost and off, is not going to be picked. So it would be nice if, what I was hoping visualizing the flow field is that eventually you could really see the flow field, the path of the flow field. It's kind of happening more mysteriously. But I think there's probably other ways of visualizing this that could be kind of interesting to demonstrate the process.
So each node or each guy has the entire flow field as its DNA.
That's correct. So it's a two-dimensional array of vectors in the example.
So it's crunching a lot of numbers to do this.
Yeah. Yes. Yes.
I think you said earlier that it's the one that gets there first gets higher priority.
Yes.
But it's not in direct correlation with how fast it gets there.
No, you're right. Yes. So I didn't actually time them and use their time to fitness, which I could have. I just quickly ordered them and said number one higher, number two. Yeah. So you're right. If it's sort of the fitness function is really here just mapped to as if they all finished in perfect lockstep timing. Yeah.
But you could use their time.
But you absolutely could use their time. Yes, for sure. The other thing about this is most of these are kind of pure, but I'm trying to, with these examples, not put any top-down thinking onto this. But you could do certain things. Like I could have maybe seeded the system with all the vectors pointing to the right start, and that might have given us at least more. We might be able to sort of see that path more clearly without it all being random to start.
And so eventually, all of these guys are going to figure out a better path.
No, there's so much mutation that I think at this point it's probably going to look like this forever. But I think we'll get some marginal improvements. Like there will be some they'll start to get a little bit faster. You're right. If I used time, that would really help. That's a great idea. Yeah, because right now it's just getting there first. If everybody's really slow, so yeah. So let me just show you this last example, and then we can kind of be finished. So I think I have a diagram that I'll just kind of use. Oh, here it is. The last example I want to show you just demonstrates the idea of a kind of more, I'm calling an ecosystem simulation, so more like the real world would work. So we have these creatures called bloops, and they're either big or small. Or they have a size. They have their DNA is one number, a single number. It maps to their size and how fast they move. So the big ones move very slowly. The small ones move very fast. And they need to eat food to survive. And there's food in the system. So if I run this simulation now, I'll leave all these running, I guess. Sorry. I can't. It's very hard to use my computer in this strange configuration. Okay, here we go. Evolution ecosystem. Okay, so let me run this one. Hopefully this will work. And what's happening here, all of these creatures, so this is, I guess, a simulation of asexual reproduction. Each creature just clones itself when it has a baby. So at any moment in time, there is a small probability that it will clone itself. So the ones that live longer just have a longer amount of time to have that happen. And one thing you'll notice here is that the system tends to evolve towards medium-sized objects. So it's not that interesting of a result. The big ones are really good at intersecting the food, but they move too slowly, so they don't really find the food. The little ones move super fast, but they're so tiny they don't seem to run into the food that often. So medium tends to be about the right kind of the perfect size to intersect the food and move about the space. And
so the food is getting randomly distributed.
Yeah, it starts with a random amount of food, and then I think when they die, they leave food. So the only thing that I find, the only unexpected result that I've noticed here is sometimes there's a cluster of big ones that just a lot of them die and there's a lot of food in one area, and then there's another big one that just keeps eating it and making new big ones. So a little cluster of big ones can kind of survive for a while in one part of the screen. So this is to me what kind of thinking through the most basic way. I mean, there's so many things you could do to a simulation like this to make it more sophisticated. For example, you could give these creatures some intelligence. I have a whole section about steering behaviors, so you could allow them to kind of see where the food is, choose to seek the food, avoid a predator. You could also add things like they only make a child when they come together for a certain amount of time. So there's a lot more that you could do with a simulation like this, but this just kind of at least demonstrates the idea there's no fitness function and there's no generations. It's just a system that lives. The circles are moving around, they live or die, and they reproduce. And eventually, I guess I added so many, it's kind of still has a lot of variety there. But if we run this for a while, you'll tend to see that it mostly ends up with medium-size elements.
What determines their movement?
I'm using something called Perlin Noise in this example. Perlin Noise is like a smooth randomness. So there's no, it's kind of a quick way to get things look like they're wandering around the screen. But now I'm kind of jumping around here a little bit, but if you're interested in this type of ecosystem simulation, I would recommend taking a look at Craig Reynolds' steering behaviors. And I'll just show you, like here's an example of one. This is all from the chapter 6 in the book. And so this is an example of crowd path following. So here are entities that are following a path as well as trying not to run into each other. So one thing that I always say as a exercise for students in the class is build a system where autonomous agents have a wide variety of steering behaviors and make the weights of those behaviors their DNA. So how much they try to follow a path versus avoid a neighbor versus seek food versus run away from a predator. See if you can evolve some type of optimal behavior. The weights for these steering forces are just hard-coded in so that they follow the path. But so combining this kind of intelligence of an autonomous agent with a genetic algorithm is perhaps something that could yield some results. Any other questions? I think I finished with all of the examples I meant to show.
So what's the state of the art with genetic algorithms? Like, where are people taking it right now?
That's a good question. I don't know that I really know the answer to that. I mean, I think there is kind of a state of the art in computer science research. For me, I see this kind of work in game design a lot with really interesting results. So you could think about if you were trying to create autonomous characters in a game that can adapt to the way a player. You could certainly use this in like museum exhibits as well. That's sort of more the space that I see at ITP at least. Kind of picking and choosing from the kind of computer science research what's kind of easy to understand and use and apply rather than kind of dig deep into the depths of the stuff.
Thank you so much.
Great. Thank you.